All right, so in this video, we are going to cover an autoregressive process. An autoregressive process is a time series regressed onto its own previous values. We're going to do an example of an autoregressive process of order 1. So first order AR process. Remember, this is for an autoregressive process. We're going to do an example of order 1. So AR1. Excuse me. So for an AR1 process, YT is going to be equal to beta 0 plus beta 1 times YT minus 1 plus our error term. And again, the error term is IID with mean 0 and some constant variance, and it's just a zero mean white noise process. And for this, Y0 would be our starting point. So we assume that the error and the current value, so let's say we assume that YT and epsilon T, our error, are independent. So we assume that they're independent. So in order for our AR1 process, so in order for our first order autoregressive process to be weakly dependent, then a stability condition has to be met. So the stability condition has to be met, and that is that the absolute value of beta 1 is going to be less than 1. It's going to be less than 1, and if this is true, so this has to be met. Our stability condition has to be met, and if it is met, then it is a stable, let's say, and it has to be met, and if so, then the first order autoregressive process is going to be stable, is a stable process. So we assume that the error term at time t and the y value at time t are independent. Then in order for this to be a stable process, or in order for it to be weakly dependent, then our coefficient, our first coefficient beta 1, or any coefficients for this has to be, the absolute value has to be less than 1. If it is, then, and if this condition is met, if the stability condition is met, then our autoregressive first order process is a stable process. And this is very important. And then to see that a stable AR1 process is asymptotically correlated, which we brought up briefly before, then it is important to assume that the process is covariance stationary. So if this is true, if all of this is true, then it is covariance stationary. And that's very important. If it's not covariance stationary, then any estimators you get will be biased, and you can't use ordinary least squares to get them. So in general, so let's write it out in a general form. So I'm going to clear all the drawings. So a general autoregressive process is going to be P, order of P. So an order of P. That's a P. I made it worse. So this is a P. So an autoregressive process order of P, and our YT is going to be equal to our intercept plus the slope of YT minus 1 plus all the way to beta P times Y lag P, and plus our error term for T, where our error term is still independent and identically distributed, and it's a zero mean white noise process. So since, so this is in general, Let's go back though. So this is the notation for a general autoregressive process. But let's go back to our first order autoregressive process where P is equal to 1. So if this would give us this model here. So it would give us that model there. So in this, since our error term, since our error term for time t and y of t minus 1 are independent from one another, then the variance, now we can do the variance of our yt is going to be equal to, so you just do the variance of each of these. So since the variance of a constant, the variance of beta 0 would just be 0, it doesn't change. So now we would have the variance of beta 1 times y of t minus 1 plus the variance of epsilon t, which is our error term. Remember, the variance of a constant is just 0. So under the covariant stationarity, so assuming it is covariant stationary and assuming that our error term and the lags are independent, this would give us this. We can factor out beta 1, so beta 1 squared multiplied by the variance of y of our process plus the variance of our error term. So because if it was, again, we're assuming that it's covariant stationary. So since it's covariant stationary, since the absolute value of beta 1 is going to be less than 1 because it's covariant stationary, and by the stability condition, we can solve for our variance of y. So our variance of y would then give us this formula. So the variance of y would be equal to beta 1 squared times, again, the variance of y plus the variance of our error term. So we can move this over to the left by subtracting both sides by beta 1 squared variance of y, which would give us this. This is equal to the variance of our error term. And now we can factor out the variance of y, and this would give us the variance of y would then be equal to the variance of our residuals, the variance of our error, divided by 1 minus our beta squared. Remember, this is beta 1. This would be the same thing if there were more lags. So the process to solve for the variance of y, the variance of our process would be the same steps for a larger order. So this is the variance of our AR1 process. And again, if this was an AR order of P, then you would go about solving it the same way as an AR1. You just have more coefficients. And then for our first moment, for the mean of y, you can just solve for it like this. This is a little bit simpler. So the mu, or the average value of y, remember mu is for y, would be equal to, you just do the expected value. The expected value of y, the expected value of the constant beta 0, the expected value of that would just be beta 0, because again, it doesn't change. Instead of skipping the step, I should write it out with the expected values. That way you can see the connection from last semester. So the expected value of yt will be equal to the expected value of beta 0, which again is just going to be beta 0, plus the expected value of yt minus 1, plus our error term of t. So the error term, the expected value of that is going to go to 0. The expected value of this is, of the intercepts, is going to be beta 0. And then you can factor out the constant beta 1, you can always factor out constants when you do the expected value, which would give you the expected value of yt minus 1. And this should be the same as this, because remember, the expected value, we're assuming that it's covariance stationary. If it's covariance stationary, then the expected value of y doesn't change over time. It has a constant mean. So a constant mean of mu should be equal to our beta 0 plus beta 1 times mu. And then you can just solve for our mean. So the mean of y should be equal to the intercept divided by 1 minus the sum of the slopes. So this is for an AR1 process, but it's similar for a larger order as well. So for this, I'm gonna clear, and now we'll talk about some of the, so we're talking about measuring serial correlation. This will finish up the autoregressive process, or the AR process. So measuring, we're gonna measure serial correlation. So measuring kth order autocorrelation. So we're gonna say kth order autocorrelation. Correlation will give us, we'll use rho for correlation. So rho of k is going to be equal to the covariance of y of t and y of k many lags. So k many lags, or whatever lag this is, divided by the variance of y of t. So the autocorrelation is going to be equal to this formula, and then you can use the empirical formulas to use it with an actual time series. And kth order error autocorrelation, kth order error autocorrelation is going to be equal to, again, we're going to notate correlation with rho, but this is going to be with error. So it's kth order error autocorrelation. And this is going to be equal to the covariance of error t with a lag of k. So the covariance between these two divided by the variance of error t. So if this is significant, if this right here, if the error autocorrelation is significant, then the model is not correctly specified. So if this is significant, then our model is not correctly specified. So this would mean that there's a problem in the model. So to test for residual autocorrelation with a lag k, you can use a t-test. So it follows a t-distribution. So to test for the significance of this, you would get your estimate for the error autocorrelation, lag of k, divide by the standard error. And I believe this was back from chapter 9, I believe, maybe chapter 8. I don't remember which one, but it's one of those where we're starting with regressions, and I think it was regression and correlation, chapter 8 chapter, or yeah, chapter 8. So the t value, the t statistic is going to be your estimate for the error autocorrelation divided by the standard error, and this is going to follow a t distribution. So with that, you can test for statistical significance. And in this specific situation, it's a little bit different. The standard error for your kth order error autocorrelation, is going to be equal to the square root of capital T, where capital T is going to be the number of periods. So this is how you can estimate it. Then with this formula, so with your estimate for your kth order error autocorrelation, and multiply it by the square root of the size that you're looking at, this will give you your t statistic, and you can test for the significance. So t, this t, that t here is going to be the number of observations if you're using the empirical formulas. And from this, now you can test for significance, or you can test for statistical significance, and you can see or have one measure to see whether or not your model may be correctly specified. So this is it for the autoregressive models, or this is it for the autoregressive model. In the next video, we will apply it to the efficient market hypothesis.